Okay, we are still working in implicit differentiation, section 3.7, page 2. And here's our first one right here. 2x cubed y minus 5 equals negative 3xy cubed, and I want you to find dy dx. So we're remembering that we're kind of tucking it away, that y is some f of x. When we look at this one right here, this 2x cubed minus y, we have a product rule here. There's the first function, and y is the second piece. When we do the derivative, the first 2x cubed times the derivative of the second, dy dx, plus the second y times the derivative of the first, 6x squared. That's just this first piece. Now, minus the derivative of the 5, minus a 0, equals, all right, now over here, again, we have a product rule. Anytime you're multiplying two things with variables in them, it's a product rule. So our first is this negative 3x, and the second function is y cubed. So plugging on through, first, negative 3x times the derivative of the second. Now here's where it gets a little tricky. This y cubed, that's like saying f of x quantity cubed. So when we do this derivative, it's 3 f of x squared. But we're not writing the f of x, we're keeping that as y. So that's 3y squared, then times the derivative of the inside, which would be f prime over here, but the derivative of that y, dy dx. Here's first derivative of the second, plus the second function, y cubed, times the derivative of the first, negative 3. Messy, messy, messy. Let's go ahead and clean this up a bit. We'll have 2x cubed dy dx plus 6x squared y equals, when we multiply here, that's going to give us a negative 9xy squared dy dx minus 3y cubed. The rest of this is all algebra. We need to solve for dy dx. So I'm going to get every term that has a dy dx in it on the left-hand side of the equal sign, and every term that does not have a dy dx on the right-hand side of the equal sign. So I'm going to add this 9xy squared dy dx to the left. We'll have 2x cubed dy dx plus 9xy squared dy dx equals negative 6x squared y minus 3y cubed. Excuse me. Again, we're solving for dy dx, so let's factor out that dy dx. Dy dx times a 2x cubed plus a 9xy squared equals a negative 6x squared y minus a 3y cubed. And then let's divide by this quantity right here to get the dy dx by itself. So dy dx is negative 6x squared y minus 3y cubed over 2x cubed plus a 9xy squared. All right, one last step. I see common factors in the numerator and common factors in the denominator. I wonder if we factor stuff out, if we can get something to cancel. In the numerator, we could factor out a negative 3y, And that will leave us with a 2x squared plus y squared. Denominator, we can factor out just an x. When we factor out that x from this first piece, 2x squared, things are looking really good to maybe cancel here, plus x times, bummer, 9y squared. Nothing cancels. Darn it. That's okay though. Alright, either one of these is acceptable. This format or the factored format. I'm still going to tell you always to factor, because if you stop here and something does factor and cancel out, then you haven't simplified that answer. So always factor and cross your fingers that something cancels out. All right? Look at this next one here. And we are looking at the cotangent of xy plus xy equals 0. And we want to find dy dx. All right, remember we're still taking y as some function of f of x. So when we start right here, cotangent of xy, cotangent's on the outside. So that derivative is negative cosecant squared xy times the derivative of the inside. Oh boy, and the inside is a product rule. First is x, second's y. Make sure you use square brackets here or parentheses to get that product rule, all of it times this negative cosecant squared of xy. So first, x times the derivative of the second, dy dx, plus the second, y, times the derivative of the first, which is 1. Again, make sure you use the square brackets or parentheses here so that this negative cosecant squared of xy goes to both pieces. All right, plus, now we need the derivative of xy. Well, hey, isn't that this piece right here inside these square brackets? Yeah, it is. So we have x dy dx plus y times 1 equals 0. And let's clean this up a bit. Negative cosecant squared xy times, now here's an option. Instead of writing this dy dx kind of as a fraction, if you will, you can write it as y prime plus y. If you like that, use it. If you don't, leave it as dy dx plus, and then this piece over here, this is x times y prime plus y equals 0. All right, now, a couple of things. You could distribute this negative cosecant squared throughout, but it's actually easier if you recognize that the coefficient of this second set of parentheses down here is a 1. Now, between these two halves, could you factor out something? Yes, we can factor out that xy prime plus a y. So xy prime plus y. And we factor that out from this first half right here. We have negative cosecant squared of xy. And from this second part, no, I didn't want that there. Silly. Sorry about that. Pulling out this xy prime plus a y, that's going to leave us with plus a 1, all equal to 0. All right, I forgot. What are we solving for? Oh, dy dx. Yep, so this y prime is what we're solving for. Well, could we right now divide both sides by this quantity right here? Divide both sides by that quantity. There are no y primes in here, so we're not going to divide out a variable. If we divide by both sides by that, this side over here is 0 divided by this mess. It's just 0. So we have x, y prime plus a y. Solving for y prime, subtract that y, divide out the x, and then the last thing, just because they said in dy dx form, so I'll change this y prime back to dy dx is opposite y over x. And that's it. Okay, one of the additional things that I do want you to notice here is that once you have an equation where x's and y's are mixed up, it's not just a y equals, so we have an equation with x's and y's mixed up, that generally your derivative has x's and y's mixed up in it. Not always, but most of the time. If the equation has x's and y's, the derivative, dy dx, will be in terms of x's and y's. Thank you for watching page 2.